Okay, the next slide just provides a listing of the tables and what they contain. Um, what you'll see here is that uh, the water table V1 actually contains multiple regions. The liquid vapor region with a T entry, which is a temperature entry, the saturated liquid and vapor region with P entry, superheated vapor, compressed liquid, and the saturated solid and vapor regions. Okay, and then the following have only saturated liquid and vapor and superheated vapor regions. These are the other tables, and Appendix B. Okay, we're going to start looking at liquid and solid states, and the main characteristic of these states is they're incompressible and a weak function of temperature. And in this case, we're going to look at the specific volume of saturated solid and specific volume of saturated liquid here, VI and VF. Okay, and what we're going to find here is that for pressures greater than the pressure of saturation, which is essentially, this line here above that line, we have a compressed solid for specific volumes equal to VI. As the temperature goes up and goes beyond a certain point, we find that we now have the specific volume of saturated liquid, and when P is higher than the specific volume of compressed liquid, then we have the surface here. Okay, so here's our surface for a solid and the surface for liquid, and these are for properties for water. These are properties of water for this example. Looking at the superheated vapor states, essentially we have this superheated vapor when V is larger than the saturated vapor value or vapor line. Okay, the region above the critical point is called the dense fluid or supercritical states. And superheated, of course, is just when you have a vapor that's being heated beyond its saturation temperature. Okay, and of course this is this area here defined, this surface or region defined with the red in this diagram. Okay, we'll look at example 2.4. This one is a rigid vessel, contains saturated ammonia vapor at 20 degrees C. Heat is transferred to the system until the temperature reaches 40 degrees C. What is the final pressure? Okay, so first part of this, what we realize here is that the volume is not going to change, so our specific volume, since it's a rigid vessel, will be constant. Okay, so we can start with going to look at table B.2.1 and find out from that the saturated, the specific volume for saturated vapor. Okay. Okay, so when we get to this table, this is B2.1, and at 20 degrees, go all the way over. Oh, this is a mistake here. This is specific volume, so this would be VG. Okay, but if we go down into the table, it's 0.14922 meters cubed per kilogram. Okay, so that's what we're starting off with here. Okay, in the second part, we're going to scroll down to the second table. Now in this case, what we're going to do is we're going to look through the table. Now this is superheated ammonia. So now there's only just one specific volume for saturation. Okay, and for saturated vapor. And if we look down here, we go down. We keep going down, we scroll down, and now we're at 40 degrees, okay? So we're looking at 40 degrees, and we get to a point here where we go over to 80 80 kilopascals of pressure, and then at 1,000 kilopascals of pressure. At this point, we see that the specific volume of saturation is lower than what we had initially. So at 40 degrees, we're going to be somewhere between these two. Okay, this value right here and the other value here. Okay, so what we're going to expect is the pressure is going to be somewhere between 1,000 and 800 kilopascals. Okay, in order to find that, we'll need to do a linear interpolation between the 2 points here and here. Okay. Okay, so from those values, I started out with the solution here. So first thing, I started with a slope-intercept form of a line, just equal to y equaled mx plus c. This is to give me the linear interpolation. And I started at, so these are my points. I'm a little bit sloppy here since I changed the subscripts for each of these. But basic idea, here's like the 800. kPa here point, and then that's where its saturation, specific volume of saturation is at that point, which I called VA. And then here's the other entry. This is the 100 at 100 kilopascals, specific volume of saturation. Saturated vapor is VB here. Okay, so this is the slope. Here's that x value, so that's like where we're trying to find it, which is in this case is V2, trying to find that pressure, and add it to C here. Okay, and that's the constant which we start with. All right, at least this is how I approached it. So the way I did it, go through that table V.2.2, look for 40 degree entries until you find the pressure with specific volume saturation is less than the initial value from the problem. Okay, so I looked through it and I found out that at 1,000 it was this 0.13868 meters cubed per kilogram, and that was at 1,000 kilopascals. And then at 1,800 kilopascals, you can see it's higher than this value here. Okay, so what this is telling me that it's between these two values. Okay, that's where I came up with the slope. So what I did is find the slope from point A to point of pressure A to pressure B, which I defined these two. This is my A and this is my B. And for the specific volumes of those, so I just plug those in. Okay, so here's my PB, PA, specific volume B, specific volume A. Came up with this number. It was a negative slope. And then X, from X is like the position from here to here, so just the difference between the two. And with that, I solve for this, which was this 5192, and then here's my x value, and then I added to 800 kilopascals, and with that, that comes out to be 945 kilopascals. So something like this, at least this is how I thought about it and how I interpreted this one to solve it. And that is that for that one. We have another problem with superheated vapor states, and this one actually uses USCS units. So it's essentially the same process as previously, except in this case you're going to use the tables from Appendix F. Okay, so we'll take a look at superheated vapor states in ideal gas states. We can start off with essentially just looking at the 2D projections on our 3D surfaces. So we have these two plots. And what we observe from these is that we have some relationships where we have simple math curves, and we have these relationships that are defined for each of these. And this occurs at high temperatures and low pressures. We have these relationships. Starting with the pressure temperature curve. The pressure is essentially equal to some constant times temperature. Okay. So you basically have a straight line here, as long as we're talking, very high temperatures and low pressures, very low pressures. Same thing here. We could do pressure times specific volume is equal to some other constant, where that constant C is just going to be a function of some initial value times that temperature. And the last curve, in this case we're talking about constant pressure, so temperature is just going to be equal to A times specific volume, and we can relate it this way with some initial, A initial times some pressure. Right? And from this we can come up with a so-called unified equation that relates the different properties. Okay? Where pressure specific volume equals R, which is ideal gas constant, and T, temperature. And then we have where R actually comes from is the universal gas constant over the molecular mass. Okay, we can use a different scaling, and if we make a few substitutions, such as specific volume is just equal to volume over mass, and then R is just the R bar over M, universal gas constant over molecular mass. And with this final substitution, algebraically we come up with this form, PV equals N R bar T. Okay. Okay, so if we look at back at this form of the equation, what we'll notice is if we just both divide this and this both sides by T, is that we're going to have since this is a constant M times R throughout the process, is that we must have a constant. It must be equal to this no matter what pressure, volume, temperature there are. So we have this relationship now that the initial relationship between pressure, volume, and temperature, where it's just pressure times volume divided by temperature, it's going to be equal to what it is in the two states, so they're identical. Okay, one thing will apply later on. Now, if we differentiate the ideal gas law with respect to time for some constant state, this is the form of the equation we get. Okay, so key part here is that pressure and temperature being constant. Where in this case, it's not defined as potentially a closed system, so we have some kind of mass flow rate. Okay. Okay. Next example is an application of the ideal gas law, and this one is just trying to determine the mass of air that's contained within a volume at a certain given pressure and temperature. And with that, the only unknown is M, so we can apply the appropriate form of the equation, which is just right here. So you have pressure times the volume divided by R times the temperature. So volume's given, pressure's given, temperature's given. The only thing you need to look up is R, which is fine, boundary here. And then you can just solve for the mass. Okay. For example, 2.8, which is another application of the ideal gas law. We have a gas bell submerged in liquid water, counterbalance of the rope and pulleys. It has a constant pressure and constant temperature, and we have a volume increase is over some period of time, and we're looking for the volume flow rate and mass flow rate of flow into the bell, assuming it's carbon dioxide. So the equation we're going to need to apply is the rate equation, okay, as we saw previously. And for the gas constant, we're also going to apply table A5. So we're taking this right from here, or from this table. Okay, so first part of this, we're going to find the volume flow rate. So we have change in volume over time, so we can determine that very easily. So in this case, well, as usual, you can determine mass flow rate just by density times the volume flow rate. And of course, density is just 1 over the specific volume. Right? Now this is pretty close to room temperature. It's at 21 degrees, and room temperature is at 25 degrees. So we can apply this equation. We can apply the mass flow rate equation. So pressure is given times volume flow rate, which we determined, and then just divided by R times T, where just make sure you have this represented as an absolute temperature. And then you can just solve very easily for the mass flow rate. Okay, so for ideal gas law, it says, when do we have an ideal gas? So essentially, for very large specific volumes. So the molecular distances are large, and you have very small forces between those molecules. Okay. And just to give you an idea, you can take a look at temperature versus specific volume diagram for water. If T is higher, you can allow smaller V's and still have an ideal gas if the temperature is high enough. Okay, this is another note. But you'll notice that these approach essentially like straight lines here as we go further out. Okay. And this gives you an idea of where the ideal gas law can be applied. Okay, now we'll introduce the compressibility factor. And really, it's a quantitative measure of deviation from the ideal gas law. And it's how it's defined. Pressure times specific volume equals Z, the compressibility factor, times R times temperature. Now, we'll do this, we'll explore the behavior of nitrogen, compressibility versus pressure. Some observations here is that as pressure approaches 0, we see that the compressibility factor approaches 1. The next, at a temperature of 300 K and above, for a range of all the way up to about somewhere around here 10 megapascals, the compressibility factor is about 1 through that range, and that means it's a good approximation for the ideal gas law within those ranges, 300 K and above, and from essentially 0 pressure all the way up to about 10 megapascals. And the third observation is that at low temperatures and very high pressure, something here, then the ideal gas law is not a good approximation. Here we introduce these reduced properties. If we were to go and plot compressibility factor for all different substances, the ranges would vary quite a bit. So here's a way to actually bring out the compressibility factors closer together. And we do this with the reduced properties of pressure and temperature. And we just define that as the pressure divided by the critical pressure and temperature divided by the critical temperature. Right? And this plot was actually done with the leak because the equations are stated. Right. Okay, so now we'll solve the problem with the compressibility factor. And you have propane in a steel bottle, 0.1 liters cubed volume, has a quality of 10%, and at a temperature of 15 degrees C. Use the generalized compressibility chart to estimate the total propane mass and define the pressure. Okay. So we're going to refer to the diagram that's given. And then we'll also have to go to table A.2 to find the critical points of pressure and temperature. Okay, so looking at the table for propane, we see it's here's the temperature, and the units are in Kelvin, and the pressure is in units of megapascals. So we go down here, and so it's 4.25 megapascals saturation, and at saturation, and then it's 369.8 degrees Kelvin. So we use that information to find the reduced temperature first, Tc, and that gives us approximately 0.78. Right? The other information we'll extract from here, reduced pressure, saturation, and the compressibility factors at the two saturation points here. Continuing on, then we can find the pressure just by multiplying the reduced pressure at saturation times the critical pressure. We come up with a value there, and then of course we use the same equation as what we did for our we're applying the same equation, the quality equation, as we previously did for specific volumes, and we're given a quality factor already, which is 0.1. So if we perform the multiplication with the information that was given to us for our compressibility factors, we come up with 0.1145. Okay. Then we apply the reduced pressure and temperature in our gas constant equation, and we also pull out the R value in table 8.5, which is right here 0.1886. That's the R value, and we plug those values in, and we can solve for the mass, which is 13.66 kilograms. Okay, equations of state. All right. So the idea of gas law is an approximation that would, along with the compressibility factor, if we want to represent the behavior over the entire region, the entire vapor region, superheated vapor region, we can use an equation such as this, or this is considered to be a class of equations, which are just generally referred to as cubic equations of state. Okay. Now, there are other models out there which we'll take a look at. With this equation, of course, there's some scale properties, which here's give you a table. Table D1 actually gives you that, the scale properties to use in this equation for the different models. Okay, so we'll look at some of these as we go along. There's some additional ones here.